Let's look at a load line problem involving a diode. In this particular problem, the diode current voltage relationship is sketched on the right of the page. It's not an exponential curve, it's a linear curve, but that's just what we're assuming this particular diode operates like. It goes up to 10 milliamps when the voltage dropped across the diode is 1.2, and it goes down to 0 milliamps when the voltage drop across that diode is at 0.6 volts or less. What we're wanting to do is this particular circuit on the left will operate at all sorts of different combinations of voltage V sub D and current I sub D. We want to find the one point that not only satisfies the circuit on the left but also satisfies the diode current voltage relationship straight line approximation curve on the right. So we're trying to find the operating point of the diode in the above circuit, or what is this, maybe we could say, what is the particular value of current, and I'll say that's I sub D star, and voltage of the diode V sub D star, that satisfies both the circuit on the left and this current voltage behavior or characteristic of the diode on the right. The way to solve this is to, if it's a more complicated circuit, you might want to find the Thevenin equivalent between the two terminals of the diode, which could be labeled A and B. In this case, it's really not necessary. We just have a single mesh. But if we wanted to, and I think you can see that the Thevenin equivalent between A and B is a 1200 ohm resistor in series with a 12-volt battery. Or in other words, we have, in terms of a solution, we could think of this looking like maybe what you're more comfortable analyzing as a circuit with this structure. Here's terminal A and here's terminal B relative to the diode. Here is now a 1200 ohm resistor, and this is now a 12-volt Thevenin equivalent voltage, which is the DC voltage that we had anyway. And we are interested in finding all of the possible combinations that satisfy this circuit for the current I sub D and the voltage drop V sub D across relative to some generic device, and then we'll find that linear relationship and intersect that with this particular IV curve on the right that the diode, this particular diode, satisfies. In order to analyze this circuit, we can now write a KVL equation for this particular circuit. It's minus 12 plus 1200 I sub D plus V sub D is equal to 0. And that's now our equation that governs this voltage current relationship of this circuit for various combinations of I sub D and voltage V sub D. Or if we wanted to, we could say that that's now this 1200 I sub D plus V sub D is equal to 12. Just another way of writing that relationship between the current in that circuit and the voltage V sub D across some two-terminal device between points A and B. That's actually a linear equation. What we want to do is superimpose that linear relationship for I sub D and V sub D on this schematic, or this IV characteristic of our diode, and it doesn't have a wide range of voltage, so maybe what we should do is just look at a couple of different voltage values and find the resulting current. And the voltage values maybe that we want to look at would be a voltage of 0 and a voltage of 1.2 with that particular relationship, and that will give us two equations in these two unknowns, and we'll be able to then sketch a straight line that satisfies this governing differential, or this governing linear relationship between the current I sub d and the voltage V sub d of this generic two-terminal device. If we let the V sub d equal 0, then plugging that into this relationship, we have 1200 I sub d plus 0 is equal to 12, or we now have I sub d is equal to 12 divided by 12 times 100, or we now have 1 over 100, or 10 to the minus 2, or 0.1 amp, which is really just 10 milliamps. We now have one point identified on this graph. We now can say, oh, for a voltage V sub d of 0, we actually have a current of 10 milliamps that flows. Let's pick one more combination, and rather than to pick I sub d equal to 0, that may give us too large of a voltage. Let's pick a voltage that's on our graph. For example, let's just let V sub d equal to 1.2 volts. If that's the case, we now have 1200 I sub d plus the 1.2 for V sub d is equal to 12, or now I sub d for this value of voltage is going to be 12 minus 1.2 over, let's say 12 times 100, or 1200. And if we do that algebra, we end up with that being 0.009 amps, or that's 9 milliamps. We now know then that for this particular circuit on the left, that when the voltage V sub d across that two terminals A and B, when it's 1.2 volts, we actually have a current flowing of 9 milliamps. And if I could then connect the dots, with that particular relationship, now what we're after is we're after that intersecting point between the blue line and the red line. And on an exam, estimation is fine. And if you look at that, that's going to be just a little bit more than 9 milliamps vertically, and it's a little bit less than 1.2 volts horizontally. It's at about the midpoint between 1.1 and 1.2. So we could say then that the actual operating point is V sub d star is halfway between 1.1 and 1.2. So let's say that it's now 1.15 volts, and the current I sub d star is a little bit more than 9 milliamps, and it's just a smidgen more than 9 milliamps. We could say, oh, it's 9.1 milliamps, and that would be a fine answer for an exam. If we wanted to, if we were given more time, if we wanted to get or obtain a more exact answer, we could actually identify the functional relationship for this particular equation, and we know what this equation is by the straight line that we've just defined. We could then find the intersection of those 2 points, and that would give us maybe a more exact or a more precise answer. Relative to the current voltage relationship of the diode, we know that I sub d is equal to, that's the vertical direction, is some slope m times the horizontal variable, diode voltage V sub d, plus some intercept b. And we can identify 2 points on that curve. We know that when I sub d is equal to 10 milliamps, that V sub d is equal to 1.2 volts. So that now says that we have 10 milliamps equal to M times 1.2 plus B. We also know that the low side, when I sub d is equal to 0 milliamps, V sub d is equal to 0.6 volts. That's also a point on that straight line that's angling up to the right. And so that gives us 0 milliamps is equal to M times V sub d, which is 0.6 plus B. Those 2 equations are valid for the particular values of slope M and intercept B. If we subtract the bottom from the top, we end up with 10 milliamps is equal to 1.2 minus 0.6, or 0.6 M, and the B's cancel. And now what might be confusing is this is a unit, and M here is a variable. So this M, maybe I should call this M a capital M. This slope, or M, is equal to 10 milliamps over 0.6, and the units on that is volts. So we now have 0.01 over 0.6, or if we did the appropriate calculation, that would now be this value of 0.0167 for the slope. Once we have the slope, we can plug that back in to find B from either of those 2 equations. From the second equation, we know we have 0 milliamps is equal to this 0.0167 times V sub d, which in this case was 0.6 plus B. And now we can solve that for the B. The B is now going to be equal to this 6 times 0.0167, which ends up being minus 10, because this 0.0167 was 0.01 over 0.6. We multiply it by the 0.6, and we have this B on the other side, or we take this to the other side, and we now have minus 0.01 for our intercept. And so now our straight line equation for the current voltage relationship on the diode is I sub d is equal to the slope, 0.0167. I sub d is now in amps, times V sub d minus 0.01. That's one of our equations, and that's the IV of the diode. That's now a straight line, and a lot of times that's an exponential curve. And we also have our equation that we found near the end of our solution in the first part of the problem, which is this particular equation right there, star. So we have 1200 I sub d plus V sub d is equal to 12. We can now put those 2 together, and we have the two equations. Our other equation, which was equation star, was 1200 I sub d plus V sub d is equal to 12. Now we can simultaneously satisfy those two equations and end up with the answer that we want, which is our desired value for I sub d and V sub d. So we now have 1200 times I sub d, which is 0.0167 V sub d, minus 0.01 plus V sub d is equal to 12. If we do the algebra, we end up with 20.04 V sub d minus 12 plus V sub d is equal to 12. If we add 12 to both sides, we have 21.04 V sub d is equal to 24, or V sub d is now 24 divided by 21.04, or that's now 1.141 volts. And that's now our value of the voltage. That's actually our operating point in a more exact sense. We can find I sub d star by plugging that value into either one of these equations. If we plug it into the first equation, we end up with our current at the operating point being slightly more than 9 milliamps, and that's then the more exact solution that we said we could find if we knew the equations for both of those operating points. And this is now our more exact solution to the earlier problem.